Hello everybody, my name is Kiran. I am working as an assistant professor in the Department of EEE, Anits, Vishakhapatnam. I welcome you all to my series of lectures on the concept of time response of control system. In today's lecture, we are going to see what is time response, its classification, that is, what is steady state response as well as transient state response, the various standard test inputs that we use in control system, and we define what is steady state error. We derive the expression for steady state error, and we also see in depth various factors and their effects on the steady state error. So the time response classification, that is, we know that the total time response of any control system can be divided into two categories. One is transient response, another one is steady state response. So first we are going to see what is time response. So the response that is given by the system, which is a function of time to the applied excitation that can be of any form, is called the time response of a control system. The next we'll see what is transient response. So the transient response is the variations in the output during the time it tries to achieve its final destination or final value. That response we call it as transient response. And lastly, the steady state response. The steady state response, as we all know, is that part of the time response which remains constant after the transient response is completely vanished from the system. So next we are going to see what are the various standard test inputs we have. The first one that we have is step input, and it can be defined as its value is 0 for t less than 0, and its value is some constant capital A for t greater than 0. And if this A value is 1, then we call this as unit step input. We denote it by U of t. And if we apply Laplace transform, the Laplace transform of the step input will be A by S. And if you consider Laplace transform of unit step input, it will be 1 by S. The second standard test input that we consider is ramp input, and it can be defined as its value is 0 for t less than 0, and its value is A into t for t greater than 0. And here A is a constant. So if the A value is 1, then we call that as unit ramp input. And Laplace transform of the ramp input is A by S square. And if A value is 1, then Laplace transform will be 1 by S square. And the third test input that we consider is parabolic input. And it can be defined as its value is 0 for t less than 0, and its value is A by 2 t square for t greater than 0. And if this A value is 1, we call it as unit parabolic input. The Laplace transform of the parabolic input is A by S cube, and if A value is 1, its Laplace transform is 1 by S cube. So these are the various standard test inputs that we are going to consider in the analysis of time response of control system. And there is one more standard test input that we all are aware of, that is impulse input, and it can be defined as its value is 0 when t is not equal to 0, and its value is some constant A for t is equal to 0. So when the A value is 1, we call this as unit impulse input, and the Laplace transform of the unit impulse input is 1. So next we are going to define what is steady state error. It is defined as the difference between the actual output of the control system and the desired output of the control system. So if I consider a closed loop control system, this is the general representation of a closed loop control system with negative feedback. Here we can see R of S is the input signal in Laplace domain, and C of S is the output signal in Laplace domain, E of s is the error that is generated in Laplace domain, and the B of s is the feedback signal, and G of s as well as H of s are the respective gains in forward path as well as in feedback path respectively. So now we are going to derive the expression for steady state error. So from the diagram we can write the expression of E of s as R of s minus B of s. So therefore E of s is equal to R of s minus B of s. But this B of s can be obtained by taking the product of the output C of s and the feedback gain H of s. So therefore B of s I can write as the product of C of s into H of s. This when I substitute in the above expression, it will give me E of s is equal to R of s minus C of s into H of s. And this C of s is obtained by taking the product of the error signal E of s and the gain of the forward path G of s. So therefore C of s I can write as E of s into G of s. This again if I substitute in the above expression, which will give me the expression of error E of s as R of s minus E of s into G of s into H of s. So this, if I take E of s common, that will give me E of s. If I take as common, it will give me E of s into 1 plus G of s into H of s is equal to R of s. That will give me the expression of error in Laplace domain as E of s is equal to R of s by 1 plus G of s into H of s. So according to the definition, we can define the steady state error ESS as limit t tends to infinity E of t. So now we know the expression of E of s, that is error in Laplace domain, that is we obtained as R of s by 1 plus G of s into H of s. And according to the definition, ESS is limit t tends to infinity E of t. So from this, according to final value theorem, we can write ESS is equal to limit t tends to infinity E of t, which is also equal to limit s tends to 0 s into E of s. We already know the expression of E of s. So if I find the expression of steady state error, it is nothing but ESS is equal to limit s tends to 0 s into R of s by 1 plus G of s into H of s. So this is the expression for steady state error. And if I observe the expression carefully, it depends on two main factors. First one, it is the input in Laplace domain, that is R of s, and the open loop transfer function G of s into H of s. Now we'll see in detail how these factors affect the steady state error. So first we'll consider the reference input, and we'll see how on the applying of various inputs does it affect this steady state error. The first one that we'll consider as step input, which has the magnitude of A. We already seen the expression of the step input, which is mathematically expressed as capital A, and in Laplace domain it is nothing but A by S. We all know the expression for steady state error, which we have derived just now, which is limit s tends to 0 s into R of s by 1 plus G of s into H of s. So in place of R of s, now if I substitute A by S, that will give me the expression of steady state error as limit s tends to 0 A by 1 plus G of s into H of s. This limit s tends to 0 G of s into H of s is always a constant. So if I apply these limits to both numerator and denominator, so in the denominator we'll get limit s tends to 0 1 plus G of s into H of s. 1 is anyhow a constant, So we'll get the second term as limit s tends to 0 g of s into h of s. So this is a constant and we call this constant as positional error coefficient. We denote this as Kp, and that will eventually give me the expression for steady state error as ESS is A by 1 plus Kp. So for a step input of magnitude A, the steady state error expression is A by 1 plus Kp. And if I consider unit step input, then it will give me the expression of steady state error as 1 by 1 plus Kp. So next we'll consider the ramp input of magnitude A. We know the expression that it is A into T. In Laplace domain, it is A by S square. So if I apply this in the expression of steady state error, that will, so 1s in the numerator will get cancelled, and it will give me eventually ES as A by S plus S into G of S into H of S. So if I apply this limit to the denominator, the first term anyhow will become 0, and the second term will get the limit S tends to 0, S into G of S into H of S. And obviously this term is a constant, and we call this constant as velocity error coefficient. We denote this as Kv. So Kv will be nothing but limit S tends to 0, S into G of S into H of S. So eventually this will give me the expression of steady state error as A by Kv. And if I consider unit ramp input, that will give me the expression of ESS as 1 by Kv. The next input that we'll consider as parabolic input of magnitude A, the expression we all know that it is A by 2 t square, and its Laplace is A by s cube. Upon the definition of steady state error, if I substitute R of s as A by s cube, so 1s will get cancelled in the numerator, then eventually that will give me the expression of steady state error as A by s square plus s square into G of s into H of s. So the first term will become 0 after applying the limits, and the second term that we get is limit s tends to 0, s square into G of s into H of s, which is another constant which we call it as acceleration error coefficient, and that is given by Ka. So eventually this will give me the expression of steady state error as A by Ka, and for unit parabolic inputs we get ESS as 1 by Ka. So these are the effects of various inputs on steady state error. The second factor that we are going to see is how a change in open loop transfer function, that is G of s into H of s, will affect your steady state error. This is in general representation of an open loop transfer function G of s into H of s, where we know that the numerator are called zeros and denominator are called poles. So here K is the resultant gain and N indicates the order of the system. If N value is 0, it is a 0th order. If N value is 1, it is the first order system, so on. The first case that we'll consider as step input of magnitude A and type 0 system. Since it is a type 0 system, there will not be any S term in the denominator of the open loop transfer function. So when I calculate the value of Kp for this open loop transfer function, it will give me a constant K. So we know that for step input, the expression of ESS is A by 1 plus Kp. So in this case, ESS value will be A by 1 plus K. Next, if I consider type 1 system, then I'll get a a single S term in the denominator of the open loop transfer function. And in this case, Kp value will become infinity because of the presence of an S term in the denominator. So if Kp value is infinity, and ESS, as we know, it is A by 1 plus Kp. Since Kp is infinity, ESS value, that is steady state value, will become 0. Next, if I consider type 2 system, you will get an S squared term in the denominator. So in this case also, Kp value is infinity and ESS value will become 0. So we can conclude that if it is a type 0 system for a step input of magnitude A, we are getting an error as A by 1 plus K, that is a constant error or finite error. And the value of positional error coefficient is constant, that is A by 1 plus K. And for type 1 system and above, as you have seen, for step input of magnitude A, the steady state error is 0 and position error coefficient value is infinity. Next, let us consider ramp input and type 0 system. So since it is type 0, there is no S term in the denominator. And here we calculate the value of Kv. We know the expression, that is the limit S tends to 0, S into G of S into H of S. So since there will be an S term in the numerator, obviously Kv value becomes 0 and ESS will become infinity since it is A by Kv. If I consider type 1 system, then there is a S term in the denominator. So Kv will cancel that S, so that we'll get the constant value for Kv, and ESS value, which is A by Kv, which is A by K. So in this case, for ramp input of type 1 system, we are getting a constant Kv value as well as a constant steady state value. Now if I consider type 2 system, there will be an S squared term in the denominator. So therefore, obviously, Kv value become infinity and steady state error will become 0. Hence, we have seen that for ramp input, if it is type 0 system, the error is infinity and Kv value is 0. For type 1 system, we have seen that it is giving both constant Kv value, that is K, and constant steady state error, that is A by K. And for type 2 and above, the Kv value is becoming infinity and the steady state value, error value, will become 0. And lastly, the third input, that is parabolic input. If I consider for type 0 system, since there is no S term in the denominator, here I'll consider acceleration coefficient, and here the value of Ka will become 0, which will correspondingly give me the steady state error value to be infinity. If it is type 1 system, then the Ka value will still be 0 and the steady state error will be infinity. If I consider type 2 system, here the terms will get cancelled, so you will get a constant value of Ka and constant value of steady state error. And if I consider type 3 system, so that will give me S cube term in the denominator. So obviously Ka value will become infinity and steady state error value will become 0. So hence I can conclude that for parabolic input, type 0 and type 1 systems, we will get acceleration coefficient to be 0 and steady state error to be infinity. For type 2 system, we are getting a constant error coefficient as well as a constant steady state error. And for type 3 and above, we are getting the acceleration coefficient value to be 0 and infinite value of steady state error. So this concludes my first lecture on the time response of control system. So in the next lecture, we are going to solve some tutorials based on the concepts that we have learned in today's lecture. Thank you.